All right, Dr. West, what does this all have to do with arrays? Well, since the heap is, I just went to William Shatner mode, sorry. It's balanced and left justified, it can be represented in an array. This can be shown as an array. You can look at it as an array. Okay, I've said the same thing many times. Watch this.
It's a box.
It's a rectangle, but it's missing the little thing over here, so it's not quite a box. Almost. We're going to take that 20, put it right here. Next comes its children, 19 and 10. Then comes 19's children, which is -2 and 7. Then comes 10's children, which is 5 and 8. All right? All ready for this? So 20's children's here, 19's is here, 10's is right here. Where would -2 left child first go?
The end.
The end. So if you want to add a node to your heap and you're using an array, it literally goes at the end. So let's give us a -4 so we don't have to reheap. So a heap can be stored as an array. And this is where things can start getting a little tricky. Now give me a number. That's not negative.
15.
15. Where do we put it? Right here. Is that a heap?
No.
No. What do we have to swap the 15 with?
-2.
All right, so we have to somehow know to go from the 15 and check the -2. How can we do that? Well, 0, 1, 2, 3, 4, 5, 6, 7, 8. Those are the indexes, right?
You go to half.
Half, you actually do index -1 over 2, which is equal to 8 minus 1 over 2, which is equal to 7 over 2. And since we don't use remainders, it's a 3. Boom. Look, a formula. Because -4's parent is 7 minus 1, which is 6 divided by 2, which is 3. Whoa. Everyone got that? So you can use simple formulas to find out what your parent is. Nice and squeaky. So we can then check, is 15 less than -2? Nope, so we need to swap them.
That's not too bad.
What's that?
That's not too bad.
It's not too bad. The reason why students have a hard time with heaps is they keep wanting to do binary search trees, which I completely understand because pictorially binary search trees make a lot of sense. Heaps have this weird heap property. You want these numbers to be sorted because you just learned binary search trees, but it's all confusing right now. That's okay. I'm sorry, was that too loud, Holland? So how do we get the parent of 3, or of 15? Well, we subtract 1 divided by 2, which makes it the 1, aka the 19. So is 15 less than 19? Yes, so we're done. Great. How do we get the child? Actually, you need to get 2 children, right? You have the left.
Add whatever. You add the, I don't know what to say.
So if we're at 19, we need to get to,
The 3.
nope, I forgot to, after I updated the array, I didn't put it in the picture. All right, so we're at 1. How do we get there?
You go.
Times 2 plus 1 and then plus 2. Like
What?
2 different separate things, like
Oh,
1
yeah.
times 2.
So left child, left child.
Yeah, okay, so times
confused.
2 plus 1. I think.
Okay, so the 19, that would get you the 15, that's great. 15, if you, let's see, times 2 would be 6 plus 1 is 7, -4. Hey, that looks pretty good.
Hey. Do you minus?
No, you did the minus up here.
Times 2 plus 2.
Oh.
Okay, that's great. Hey, you now know how to get the children inside of an array representation of a binary tree.
Is the tree always an array?
When you use a heap, you want to use an array. That's the whole point of using a heap. So you don't have to do your nodes and pointers. What's another advantage of using a heap as an array? Oh, we haven't gotten to that, so we'll get to that in a moment. Sorry.
Can we use vectors instead of array? Or is that like a
Yeah, it's the same thing.
Okay.
Vector,
It's just a fancy
I
array.
have a question.
yes. Hold on, one moment. Yes, Sam?
Wouldn't you have to reallocate memory whenever you add?
Yeah, if it gets too big, then you have to reallocate. That is correct, yes. But in general, when you use a heap, when you use a heap, you usually call heapify in order to take advantage of this property. So yes, there is, on insert, there is a chance it becomes O of n, but since this is usually for critical time applications, you usually set, all right, we're gonna have 4,096 open slots. If it goes beyond, we're gonna just guarantee it never gets bigger than that by the way we program. Everyone's cool. Great question though, great question. Yes.
No, it was roughly the same question I had, is that
No.
what if you like exceeded the minimum?
Yeah, then you have to recreate the entire array. That's correct.
Yeah.
So there are times, like I said, this is something you keep in your back pocket because there's going to be times where the heap just is a perfect fit for certain things, especially when you start doing graph algorithms. Unfortunately, we're only going to get to 2 graph algorithms in this class, but when you take regular algorithms, there's going to be times where the heap just makes perfect sense in the middle of your graph algorithm. And there's other situation, which we'll get to, that makes perfect sense in this class, which makes our hard problem become super easy.
So why don't you teach this one before the binary search tree?
6 of one, half a dozen of another?
What?
What would be the point?
I like this one better.
You like this one better?
Yeah.
Huh. You're the first student to say that. Everyone looks at me like, this is confusing.
Actually, all of these students.
What's that?
All of these students.
Huh. All right. Oh, still got plus. Let's move that down just a little. There you go, people at home. All right, then we can repeat till it's all right. Great. So sorting. So how do we sort an array with this?
Make a sorting function that sorts it.
Just
Nice.
go through it.
So what's the first thing you do to all the elements?
Bubble sort.
It fixes everything.
Learning what we just learned, applying what we just learned. What's the first thing we want to do?
The element at index 0 is going to be the greatest, so you already know that one.
Mm-hmm. And then you add the next one.
You just keep doing that.
Right, so you heapify the array, that is the term, and then you remove them one by one. So let's watch that pictorially. Because the binary tree is balanced if justified, it can be used as an array, just as I said. Heapify the array while the array is empty, remove and replace the root and reheap the node. So mapping into an array. Hey look, it's like what I just did, only the indexes are a little off. See? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, well, you see what happened.
They just gave up.
They just kind of gave up, yeah. Oh well, sorry about that, I think.
His tab key wasn't working
So-
that day.
It was not.
So just to clarify for line, so pretty much delete everything in the heap, put it into array, then heapify it, and put it back into the heap.
So what's actually going to happen is if you have an array of elements, you're going to start with the leftmost node, and that's already a heap, so that's great. So you add the next element by shifting your range from 0 to 1 and pretend that's a heap and fix it, maybe sift up. Then you add the next one, sift it up, add the next one, sift it up, sift it up. So really, if you want to take an array and heapify it, you just start here and then you run sift up on each node running to the right. Now how long does that take in big O? Each sift up takes, it's n times how long it takes to sift up, which is,
In log n?
so it's n log n. So sifting up in the beginning is n log n. And let's see where I'm on the board. So, oh, I have plenty of room over here that I'll just get in the way with my body. All right. So heapify is, O of n log of n. All right, and that's the take an array and heapify it. Notice that unlike merge sort, we are not consuming any more memory. So this is an in-place algorithm so far, which is great. All right, so we're still talking about how we map to array. Here are those formulas we wrote up on the board, just to confirm that we are correct. That way I didn't forget something. I have written them on the board. It's very important. That way you know what the left child and right child is. Knows that this is based on the index. So you're at 17. You want to know what the children of 17. It's 2 times 2. 2 times index, so 2 plus 1 is, so it's 5, 14, and then 15. And then for 14, index 5, so it's 2 times 5 plus 1, which is 11. So there's that 9, and then plus 2 to get the index at 12, which is 11. All right. Whew. Yeah, so there's some more examples. Great. Removing and replacing. The root is the first element in the array. The rightmost node at the deepest level is the last element, so you swap them. So if you want to remove the 25, you swap it with the last one and then pretend that the heap is back to what it is. Or it only goes from 0 to 11, not 0 to 12. Notice that we put the largest element on the right. And then we're now going to sift up the 11 and pretend that the last cell no longer exists. So then we reheap.
Shun the 25.
So, yeah. So just keep a track at home. Remember that the children of 0 is 1 and 2. You pick the larger, which is the 22, so you swap the 11 and the 22. So that would have an 11 right here, except for you want to find out what the two children, of 1 is, which is 2 times 1 plus 1. So that would be the 19 and the 22. So you need to swap the 11 with that 22. And then, so you're at 4. And then here you have 11. Your two children are going to be 9 and 10, which is 11 and 3. So we're going 11 and 3. Yeah, 11 and 3. Where was I? Oh, no, here. I'm sorry. Looking at the wrong one. 11 and 3. There we go, which is actually 21 and 3. Sorry about that. So you swap the 21 with the 11, and then there is the 11 percolate down. If that was too confusing, you may have to draw it out, but it did percolate or sift down the 11. And notice that the largest one is at the end, 25. So, in order to remove an element, you are swapping and then running sift down, which is log of n. So removing one element is log of n. So if you want to remove all the elements, it is in log n. So remove all elements is O of log, n times log of n.
It basically just puts it in reverse order.
Yeah, reverse order. And then it's going to keep doing it. And it doesn't actually show you. Wow. Okay, if you kept doing this, so next would be, you'd swap the 22 and the 9, and then you sift down the 9, and you keep repeating it until all the elements were from 25 all the way down to the lowest, which would then be sorted. So what's the big O of this in total? Well, it's the heapify, which was n log n, plus the removing all elements, which was n log n.
So it's 2 in log n.
Right, we don't care about coefficients, so it's just n log n. Right. Notice that this was done in place. There was no need for extra memory like with merge sort.
Real quick.
Yes.
When you do sift down, you grab the greater of the two
Yeah, you always grab the greater. That way you don't have to search down the other tree or anything.
So 9 would grab 22, and then from there it would grab.
22 again. 22 again, yeah.
I thought my eyes were deceiving me. No.
Nope,
Is it
no.
really?
This heap has multiple elements of the same value.
You always compare the root to its two children, and then you pick the better child.
You pick the larger child, and the better is always the larger. Actually, the better is whatever the heap property is. Because one thing I haven't mentioned is the heap property so far is larger. You can define the heap property to be whatever you want.
Oh no.
But we're not going to do that today. We're going to stick with larger because it's already a little confusing as it is. But keep in mind that you can stretch this to be any heap property. In which case, when you want to go sort it, it will sort it from the large, whatever your heap property down to the lowest. Whatever you define your heap property to be. Because you could have it based on the reverse of the smallest. If you wanted to, it would work the same way, just it'd be heaped that way. All right, so their analysis, heapify, and then each node. Oh, how long does it take to heapify? We add each node, and each time you add a node, it's log n, so it takes n times log n, so n log n. Here's the rest of it. While the array is empty, remove and replace the node and reheap it. We do it n times, okay, n minus 1. Removing and replace the root takes O of 1 because of the swap. So swapping is always O of 1 because of the set number of operations. Therefore, the total time is n times however long it takes to reheap. Well, reheap is a log of n, as we talked about. So reheaping is n log n, like we just said. Heapify, while the array is empty, remove and replace and reheap. We have seen heapify takes n log n. The loop is n log n times, so you add the two, which is just the same as n log n. The end. Great. How are we doing? All right, what do you think of heaps? You already said it was better than binary search tree, which was
It's not the worst thing we've done.
that's not the worst thing. Oh,
What
that
was
just
that?
begs the question. What's the worst thing we've done? I think I know the answer.
Honestly, not sure at this moment. I have to think about it. My brain's not completely.
Oh, I thought you were going to just say project 1.
Ooh, that's a good one.
And having to parse that HTML file was
It's good practice, though. Very good practice.
And when do you use the parsing and everything?
When you use parsing, you mean like the compiler has to parse your file? Or whenever you want to do some type of static code analysis, you have to parse the input. Whenever you wish to validate a user's input into your program, you need to parse it. Yeah, parsing's everywhere. We're not getting around parsing.
What about the
Doesn't that be a good point?
spider search?
A spider search? So how often do you have to do a search? Or, well, actually it depends on which search you went with. I almost gave this one away. Ooh, that's close. When do you need to search the space of available elements? A lot. You have graph, or we haven't done graphs yet. Woo. Google Maps is a giant graph. You're asking because you have multiple nodes with arrows pointing to each one. How do you find, or how do you search the shortest path from one to another? There's an example right there. It comes up a lot in graphs. We will get to
Did you
graphs.
work on Google Maps?
No, I worked on Android. So I was the one that made sure Bluetooth, Wi-Fi, and telephony work, and I actually integrated some of the later, more advanced features of Bluetooth.
What kind of phone do you have?
Android.
That was funny.
No, I don't need to spend that much money on a phone. It's a phone.
True.
Actually, sadly, the thing that gets me most about Android is they have the, what's it called, Google Rewards. So you just do those surveys, and then you have money to just buy whatever app you want.
What?
What?
Or
Do
you
you have
just
an
don't
iPhone?
buy it.
Yeah.
Oh, yeah.
Sadness.
I think I have $43 right now.
What?
Yeah, I have $43 to just buy whatever app I want. Yeah.
I've never heard of that.
Oh, it's great. You have it, or? Yeah.
I've never used that. I just don't buy apps. I just get the free ones.
Well, the reason why I like it is because you can get the free ones and you usually spend, $2 or $3 to remove the ads. So do I rather answer questions about, where I've been? Usually the questions are like, hey, did you just visit this store? Yep. Did you use your credit card? Yep. Can I see the receipt? Nope. All right, here's 30 cents.
Can I get your credit card info?
Yeah. No? Here's 30 cents. Okay, thanks, Google. And you do that, you do that 10 times. Now you don't have to watch ads on whatever app you want.
It's crazy.
And you can buy some of the other ones because I'm still learning some Japanese, so there's a couple of apps that are really helpful if you pay a little money for it.
I love how you said 10 times, but then the money you had been 100 times.
Oh yeah, well, I've done this for what, 2 years, 3 years, and I've already spent the money multiple times. I mean, the survey takes what, 15 seconds? It's not hard.
Free money, basically.
Well, it's not free because it takes 15 seconds.
Still worth it.
But it's
like
worth it.
watching an ad and getting paid for it.
Yeah. Well, I mean, I can either pay for get annoyed by the ads in my apps, or just do a survey real quick. And most times, like, oh hey, look, I have a survey. I wonder if I don't have a survey right now, do I?
Money.
Nope, no survey right now. No, they ask you other questions like, did you like this YouTube video?
No.
Here's 10 cents. They seem to always give you at least 10 cents. And I have gotten over $1 before.
Does it take the same amount of time, or is that one typically longer?
And the video one is the video one says, based on the description, do you think this is a good video? Rated from 1 to 5 stars.
Zero. It's garbage.
The first time you do it, I think they give you $2 because they test to make sure that you're actually paying attention and not just hitting buttons. So, well, now that we've talked about that was a great diversion. Back to Heaps. Any questions about Heaps? All right.
Is the heap typically stored in the heap?
Good question.
Ooh.
Way to confuse everybody.
All right. What's the answer?
It
Yes,
depends.
because-
Yeah. Yes. Yep. They can be stored anywhere, but it depends on what you're doing. If you're running a graph, most graph algorithms, they generate the heap dynamically because it's part of the algorithm. So that would be on a heap. If you're in a real-time application, they usually allocate it statically inside of general memory, so you can put it there. Other times you might have a system library that just allocates it on the stack in order to do your quick heap analysis. So it depends. It doesn't. Any other questions? Great question. All right.